Last lecture, we were looking about solving differential equations of higher order, homogeneous with constant coefficients. In this same section, we're going to cover also the higher order, that is degree 3 or above. All right? So let's see. So unlike looking at a separation of variables or something like the exact equations or something like that, actually, as you could tell, solving one of these differential equations doesn't even require any calculus at all. It's all algebra. All you need to be ready with, guys, is all your factoring techniques, difference of squares, trinomials, sums and difference of cubes, also solution of polynomial equations using the rational root theorem, which includes not only the reals but also the complex ones. So we're going to get through many of those. Thank you. Okay, so well, I showed you the derivation of how we propose a solution y equals e to the mx. And guys, I'll show you later why this works for this kind of equation. It's not just because I like this function, so I wanted the solution to look like exponentials. No, there's later we're going to reflect on why and how this works. All right, and we had three cases. One case in which the root of the second order, or rather the quadratic equation, are real and distinct. Well, all we do is a linear combination of exponentials with constant c1, c2. Where the coefficients of the exponential m1 and m2 are the solution to the polynomial equation. Well, actually, we already did two examples of those, right, before the end of the lecture. Let me go back to the summary. So far we have solved a couple of this. Case 1, okay? Now, let's have a look at one more example. Okay, example letter C, y double prime minus 10y prime plus 25. What do we do? So the second derivative term becomes an m squared minus 10 times, instead of y prime, that's m to the first power, but the y doesn't have anything, just the coefficient, plus 25 equals to 0. Well, let's factor this trinomial. Well, factors of 25 that add up to negative 10, are there any? So m minus 5 and m minus 5. Well, do you guys see this is a repeated solution? So this is m equals to 5 repeated. Well, in this case, because the solution is repeated, this cannot be just a y equals c1 e to the 5x plus c2 e to the 5x, because actually you could combine these two together, and in fact, if you think of e to the 5x and e to the 5x itself, actually those two form a linearly dependent set of solutions, right? What do you have? Well, if the coefficients are 1 and 1, remember the small, medium, and large fry or drink from your favorite fast food chain? Well, so this linear combo is going to have two items of the same. So that's not how we're going to give the solution. So what do? We're going to multiply the second one by a power of x. We're going to get deeper into this multiplication by x later in the example. So that's one. All right, that's another example. Okay, again, factor your polynomial, write your solution, check what case in particular that is. No calculus, no integration, no derivatives at all, just algebra. All right, example letter D. Okay, let's write the characteristic equation or auxiliary equation. It's either way you want to call it. M squared plus 4m plus 7, let it be equal to 0. Okay, so first thing we try every time we have a quadratic equation, can we factor it? So let's use the double bubble method. Factors of 7 that add up to 4. And I'm afraid this is not going to be possible, right? Because factors of 7 are 1 and 7, or negative 1 and negative 7. But none of those combinations add up to positive 4. What do? Quadratic formula. So m equals minus b plus or minus the square root of b squared minus 4 AC, everything divided by 2a. Well, what is this? Negative 4 plus or minus the square root of negative 4, quantity squared, minus 4 times a, which is 1, times c, which is 7. Everything divided by, what is that? 2 times 2a, which is 2 times 1, okay? Let's simplify the radicand in one shot. Okay, so well, not in one shot. Negative 4 plus minus the square root. That is 16 minus 4 times 1 times 7. Is that 28? Yes. Divided by 2. Okay, plus, oh, wait. Negative 4 plus or minus, Negative 4 plus or minus the square root. 16 minus 28. Is that negative 12? Ooh. Negative radical, okay, negative 12 over 2. Okay, we'd better simplify these guys in terms of complex numbers in the form alpha plus beta I. All right, so in some of these complex solutions, we may need to work with simplifying these radicals for a few steps. Okay, so this is, what is that? Negative 4 plus minus the square root of, okay, the number negative 12, isn't that the same as negative 4 times 3 divided by 2? And well, we can factor out, okay, we can factor out the 4, take out the square root of 4, which is negative 4 plus or minus 2 times the square root of negative 3. Everything divided by 2. However, what about the negative inside of the radical? What do we do with that one? What is that? The imaginary unit, right? So that'll be negative 4 plus or minus 2i square root of 3, and everything divided by 2. Lucky for us, both the number 4 here and these two multiplying the I and the radical are divisible by 2. So keep going. So that's negative 2 plus minus I square root of 3. So now that we have simplified the complex number in the form alpha plus minus beta I, because that's what we want to know what it is, what's alpha, which is negative 2, and beta, which is square root of 3. Okay? All right, so when we look at the forms of the solutions, this is actually case number 3. So whenever m1 and m2 are complex roots, so we're going to multiply e to the alpha x times c1 cosine beta x plus c2 sine beta x. All right? That means the following. That means y equals to e to the negative 2x times c1 cosine of square root of 3. Actually, be careful. Make sure the x doesn't get inside of the radical. Plus c2 sine root of 3 x. Okay. Root of 3 times x. Okay, and we can call it a day for the solution here. All right. I mean, typically, you may express this as distributing the exponential, but this is fine as well. I mean, we're factoring the exponential, and we that's in a way simplified, if you will. Okay, so far we have done a couple of exercises of each case. So actually, I would like to show you the derivation of why do we multiply by x whenever we have a repeated root. And I also like to show you the derivation of the cosine and sine. Okay, let's go back to the previous page. Okay, so that's actually the page we left blank. All right, so let's analyze case 2. Repeated real solutions. All right. So consider the equation am squared plus bm plus c equals to 0. All right, I'm going to divide both sides by a. Okay, dividing both sides by a would actually take us to m squared plus b over a m plus c over a. Okay? Now here is the thing. Let's get one of the important and crucial pieces of information for the derivation. Of course, what happens if you solve this polynomial equation? This means, because we're going to have a repeated solution, I'm just going to call this m1 equals to minus b plus or minus the square root of b squared minus 4ac. Okay? Everything divided by 2a. So here, I'm going to simplify the solution to the algebraic equation by doing the following. Check this out. So I'm going to set this guy equal to 0. Why is that equal to 0? Because whenever we have two equal solutions, that's because the discriminant is equal to 0, right? We discussed that in the previous lecture here. So M1 and M2 are real and repeated whenever the discriminant is equal to 0. Okay, so from here I'm going to get the following. M1 equals to minus b over 2a. And just for fun, I'm going to keep only the minus b over a equals to 2m sub 1. You'll see why I'm doing this. Let's actually save this for later. Okay, I'm going to put a star to it. Save it for later. Okay? Okay, guys. Well, so that means we will have one solution to the differential equation. Y equals to, what is that? E to the m1x, right? Whenever we have a repeated solution, so that's what we get. And again, we cannot just write the two of them together. That actually combines them together. That's gonna be weird. The question here is, how do we get the other solution? Knowing one solution. Which one? What do we do? We did it last time, actually. If you know one solution, you can get another one by reduction of order, right? Well, let's use reduction of order. So y sub 2 equals y sub 1 integral of e to the negative integral of p dx divided by y sub 1 squared dx, okay? So what is y1? This is simply e to the m sub 1 x times the integral of e to the, oh wait, what's p in, oh yeah, what's p in this equation here? B over a, right? B over a dx. That's negative the integral of, that's me. Negative the integral of b over a dx. Everything divided by e to the m1x quantity squared dx. All right? Okay, so the integral of this constant will be, well, that's e to the m1x, integral of e to the negative b over a x. Everything divided by e to the 2m1x dx. Do you guys agree with this? All right. Remember we saved this for later? Remember this? All right? Remember we said we're going to use it for later? Well, it's now or never, guys. Substitute this coefficient with a 2m or 2m sub 1, okay? And so m1x integral of e to the 2m sub 1 x over e to the 2m sub 1x dx. Well, let me just highlight so you can keep seeing how this got replaced, right? Well, boom, this reduced. This is e to the m sub 1x integral of dx, which is the integral of dx. This is x e to the m1x. This is how. So knowing one of the solutions that gets repeated, use reduction of order to get the second solution. All right? Okay, guys, now the interesting one, the fun one, is the next one. Where is this conjugate complex root coming from? Why do we, whenever we get this complex solution, why do we have combinations of exponentials and trigonometrics? Okay, so, I mean, Just so you know, actually, because do you guys agree that you're getting a conjugate pair of complex numbers which in a way are distinct, right? So that's very similar to the first case when we have real and distinct solutions, except that these are complex. Okay, so this means that if you have m sub 1, alpha plus beta I, and m sub 2, which is alpha minus beta I, okay, just write it as if you were, write it in terms of exponentials like y equals to c1 e to the alpha plus beta sub I, and beta I times x plus c2 e to the alpha minus beta I times x. All right? So that's the solution, right? However, well, we're gonna do a little bit of algebra here to turn these imaginaries in terms of exponentials. Okay, what's the sorcery here? Well, let's see. So number one, how about do you guys agree this is C1 e to the alpha x times e to the how did I do? Okay, beta I x plus C2 e to the another alpha x times e to the negative beta I x. All right? So, and then how about we factor out, what is that? The e to the alpha x. E to the alpha x times C1, okay? Let me actually make some room here. I'm going to need it. And C1 e to the I beta x plus C2 e to the negative I beta x. Okay? Actually, guys, just so you know, we're actually doing a little bit of higher levels of mathematics. We're doing complex variables, complex analysis. You know, it's this subject I've been mentioning a few times before. You're going to use it in your upper division courses, engineering, mathematics, you name it. Okay, so, but actually, you already know some complex analysis from pre-calculus or trigonometry. Remember Euler's identity? Okay, Euler's identity. Using Euler's ID, that is e to the I theta equals cosine theta plus I sine theta. Remember that one when we were writing complex numbers in terms of in exponential form and trigonometric form? You use this identity back in trigonometry. Actually, how do I do this one? Okay, let me actually do the negative. E to the negative I theta equals to cosine of negative theta plus I sine negative theta. Okay, well, cosine of negative theta, it's actually still positive cosine theta plus, but because sine is an odd function, that negative goes outside. And actually that plus actually becomes a negative. So cosine, because it's an even function, evaluated a negative result, you get the same positive result. Okay, so let's replace. Okay, I'm going to replace actually I'm going to use different colors instead. Let me change the second one with another color. Okay. So I don't lose you with all these substitutions we're going to do. Okay, so I'm going to replace the e to the negative I bx with all this, all right? And with a different color, with green, the color green, the positive version. Okay, I'm just trying to color code what we're going to substitute. Okay, so number one, we said, so coming back to y, okay? Coming back to y, this is equal to, okay, we said, I believe okay, no, C1, okay, or C1 e to the alpha x, okay, I'm actually replacing, I'm taking the C1 outside only, and I'm going to multiply by, cosine beta x plus I sine beta x. So that's using Euler's identity with the positive argument, with the positive exponential, which becomes all positive arguments, plus C2, okay, plus C2, e to the alpha x cosine bx minus I sine, not b, beta x, all right? Okay, what do we do here? So I'm going to factor out the exponentials once again. So e to the alpha x, okay, this is times c1 cosine beta x plus I. Actually, I'm going to do c2, okay, c1 I sine beta x plus c2 cosine beta x minus c2 I sine beta x. All right? Okay, let's see how can we simplify all this madness here. Okay, I'm going to factor the cosines first. I'm going to do another factoring here. So that's y equals to e to the alpha x. So the cosines, cosine beta x. Do you guys agree this is c1 plus c2 cosine beta x plus c1 minus c2? Actually, I'm going to keep the I. You know what? I'm going to keep C1I minus C2I sine beta x. Okay? Well, C1 plus C2. What is that? Remember, by absorption, a constant plus another constant is just another constant. Okay? So, this guy equals to C1. And these other constants here, including the I, just call it another constant. Yes, the I is there, but we all know this is coming from some complex function here, right? And well, this is y equals e to the alpha x times c1 cosine beta x plus c2 sine beta x. This is where all this is coming from, right? It's a bit of complex analysis. Nothing new for you, because this is something you did back in trig or in pre-calculus. Put it together with these real roots, with these equations. This is where it's coming from. All right. Actually, there's something else I'd like to mention here. All right. So what do we have? Three cases. And this is going to be very useful for applications of this. Whenever alpha is less than 0, alpha equals to 1, and alpha is greater. Well, actually, let me do greater than. Should I do negative? Yeah, negative and positive, greater than 0, positive. Okay, I'm not sure if alpha is 1. Okay, negative 1, and let me do greater than 1, right? Let me do greater than 1. Okay, so what's going to happen here? So actually, if alpha is a negative, it's a negative coefficient. So we have an exponential with a negative exponent, which actually gives us a decreasing function, isn't it? So decreasing, or we call it underdamped. Underdamped. If it's greater than 1, okay, that's increasing or overdamped. And while this decreasing and increasing over time, we're talking about oscillations. However, when oh wait, no, when this is equal to 0, let me change my mind. This is equal to 0, greater than 0, less than 0. Alpha is equal to 0. Yes, undamped. Just undamped. We're going to talk about this in a second. Well, actually, we can do that. We can do this right now. So if we graph, if we graph the solution to the differential equation we just did in the last example, right here, we can do this one. Okay, let me graph this function. I mean, I'm gonna choose C1 and C2 to be 1 so I can actually show you a graph. And actually, let me just change the coefficients to nice numbers. Okay, so let's go Y. Okay, no, second quit. Window. No, mode. I'm going to go function, and y equals to, okay, I would like to shut this one down. Okay, let me do second e to the, okay, let me do e to the negative 2x, all right, e to the negative 2x, and then I'm going to multiply this by cosine 3x, close parentheses, plus sine 3x. Okay. Let me close parentheses for the trick and for the whole thing right here. Okay, so graph. Well, I'm not going to be able to see anything. Zoom fit. No, zoom standard 6. Okay. Okay, so actually we have a decreasing function because of the negative exponential. Okay. But actually, I wanted to do something else. Let me see if I can zoom out. Even more zoom out. No, this is not working the way I want it to work. Cosine 3x, sine 3x. Okay. Oh, you're right. Mode or window. Thank you. Mode. Oh, it's in degree, that's why. Thank you. This should be in radians. Okay, graph. And this is what I wanted to get. Okay, let me do zoom standard, number 6. Okay, do you see how we have these oscillations and then the oscillations get smaller and smaller and smaller? Well, that's because we have somehow this decreasing here, right? This decreasing. Or some convergence to some steady state in the long run. Okay, let me change the sign. Let me change the sign of the negative 2 to a positive 2. Okay, let me delete the sign and graph. Now we're going to see the other way. Now these oscillations are going to get bigger and bigger. So now we're going to have an overdamped behavior. Okay, so y equals, let me change this to a 0. Let me see if the 0 is taken. Hopefully, what do we get? Okay, just a regular oscillation. It's underdamped. It goes up and down because what we have, a combination of sines and cosines. So we should see these waves right here. All right, so that's something we're going to look at when it comes to solutions to differential equations with complex roots. Okay, so okay, well actually what do we have so far? A few examples, the derivation, where the cases come from, the behavior of this very specific combination of tricks with exponentials. How about we solve an initial value problem? All right, so these are going to be interesting ones to solve. Okay, so solve for y double prime plus 4y prime plus 17y equals to 0 with initial condition y of 0 equals to -1, and now we're going to have a second condition because what are we going to do? We will have to find two constants, two unknown constants C1 and C2, so we need an additional condition here. Why? That'll be y prime of 0 equals to 2. Actually, it doesn't have to be y prime. Maybe it's a y of 1 equals to 3. Maybe it doesn't have to be the derivative, all right? Just so you know. Okay, so, but actually this is the derivative. And it's like this for a reason, actually. Okay, so let's write the auxiliary characteristic equation. Is that 4m squared plus 4m plus 17, is that equal to 0? Okay, oh, can we factor this one? I don't think this one is going to be easy to factor. Okay, 4 times 17, is that 34? Times 2, is that 68? Factors of 68 that add up to 4. No, I don't think it's going to be factorable, this one. Okay, so another quadratic formula. So m equals minus b, that's negative 4, plus or minus the square root of 4 squared minus 4 times 4 times 17. Everything divided by 2 times a, which is in this case 4. Be careful. Most of the times a equals to 1, but not in this case. So negative 4 plus or minus the square root plus or minus square root of 16 minus 4 times 4, which is 16 times 17, big number, 272. You have a calculator with you guys? Well, you can verify this result. Everything divided by 8. All right? And well, 16 minus 272, negative 4 plus minus square root of negative 256 divided by 8. And actually 256 is a perfect square, isn't it? That is 16, isn't it? 16. So negative 4 plus or minus 16, but because it's with a negative inside of the radical, 16i. What do we do here? Keep dividing by 8. Okay, and well, we need to write this complex number. We need to split this number. So negative 4 over 8 plus or minus I times 16 over 8. Well, 4 over 8 is that negative 1/2 plus or minus 2i. So what do we have? Alpha equals to negative 1/2 and beta will be 2. By looking at the sign of alpha, what do we have? We have an underdamped behavior, undamped, or overdamped. What's that going to be? It's going to be an underdamped, right? It's going to oscillate and then, but in the long run, it's going to get to a steady state to converge to some value there, all right? Okay, well, so let's write our solution. Okay, so y equals to e to the alpha, that is negative x over 2. I'm going to write it as negative x over 2 or negative 1/2 x times c1 cosine 2x plus c2 sine 2x. All right? I'm going to leave the solution like this. I think we could distribute if that works, but actually, I don't want to do that right now. Okay. So actually, let's take the derivative of this. Okay, let's take the derivative of all this. Y prime equals to. So in this case, we're going to need the product rule because we have the product between this function and this bigger function inside of the parentheses. And that's why I had the exponential factor in the front. I mean, again, you can distribute if you want. However, if you do that, you will have to deal with 2 product rules instead of just 1. All right? I think this is going to be more efficient. So derivative of the exponential, which is negative 1/2 e to the negative x over 2, times everything else without differentiated. Plus the derivative this time of the second factor, which is what's inside of the parentheses. That is, I'm going to leave a space for something here. That is negative c1 sine, c1 negative, actually negative 2, okay, negative 2 c1 sine 2x plus 2 c2 cosine 2x. Okay, guys, here be careful. Although You might be thinking, oh, should we keep everything C1, C2? No, in this case, we don't absorb the constants. We need these coefficients for a big reason, okay? You'll see why in a second, okay? So yes, those are, okay, the solution. Actually, this is the general solution. That's the derivative of the general solution. Why are we taking the derivative? Because it's time to find the constants of integration using the initial condition for the function and the initial condition for the derivative. That's why we had to take the derivative. I mean, oftentimes you could have been given maybe the fourth derivative of 0 equals to 7. Well, then we would need to find the fourth derivative. Why? I don't know, but maybe just to mess with us, I guess, right? I don't see another reason to this, okay? Let's see. Okay, so with y of 0 equals to 1, okay, so y of 0 equals, evaluate the solution at 0 e to the negative 0 over 2, c1 cosine 2 times 0 plus c2 sine 2 times 0, which is, okay, yes, y of 0 equals to 1 equals to e to the 0, which is 1, okay? How about we cancel some terms here? So sine of 2 times 0 is going to be 0, and that's going to leave us only with c1 cosine of 2 times 0, which is going to be cosine of 0, which is 1, but 1 times c1, that's simply c1. All right, oh, actually this is negative 1, right? Negative 1. Negative 1. And, well, what is that? Simply, oh, we got it, right? C1 times, oh, actually, let me indicate this goes to 0, this goes to 1, okay? So we can justify our final result here. Okay, so that's C1. We're going to use the initial condition for the second derivative to get C2. All right, yes, it's going to be a bunch of substitution with plugging chuck here with y prime 0 equals to, that's equal to 2, right? Equal to 2, and okay, we will know already that C1 equals to negative 1. Okay, we would already know that C1 is negative 1. Okay, so what we're gonna do here is, well, let's keep this. Keep the C1 for later. So, y prime of 0 equals to, what is that? Y from 0 equals to negative 1/2 e to the negative 0 over 2 times, oh, it's going to be a mess, c1 cosine of 2 times 0 plus c2 sine 2 times 0 plus another e to the negative 0 over 2 times negative 2 c1 sine of 2 times 0. Okay, let me make this bigger, plus c2 cosine of 2 times 0. Okay? Okay, let's zero whatever we can zero out already. Alright? 0, this is equal to 1, this is equal to 1, this is equal to 1, and this is equal to 1. Alright? Okay. So let's see what are we going to be left with. So y prime of 0, which happens to be what? 2, equals to, what is that? Negative 1/2 times 1, which is negative 1/2. Let's see what survives the cancellation in the first group of parentheses. So all this cancels out, leaving us with c1 times 1. Agree? Over here, well, the exponential becomes a 1. I'm not going to write that 1. However, what survives the cancellations inside of the second group of parentheses is only the 2 times c2. Okay? So plus 2, c2, and that's it, right? Well, so we have one equation with two unknowns. However, what do we know about c1? Did we get it before in the first computation of the initial condition for the solution to the DE? Okay. So let's substitute. So from here it follows 2 equals to negative 1/2 times 1 plus 2c2. Okay, so negative 1/2 times 1, isn't that positive 1/2? I'm going to add 1/2 to both sides. And that's going to take us to 2c2. 2 plus a half, isn't that 5 halves? Yes. Which one? Yes, yes, you're right, you're right. Negative here, right? Negative. And so that means we need to subtract, right? Instead, thank you. So this is equal to 3 halves, right? And then divide both sides by 2, C2 equals to 3/4. All right? And we're not done yet. We're not done. Particular solution. That'll be y equals e to the negative x, and then negative x over 2 times negative cosine 2x plus 3/4 sine 2x. We're not done yet. We need to box our final answer. Got him that one. Oh my God. Now think about the 3x3, the C1, C2, C3. We're going to do one, of course. We're going to do one of those with 3. So wake up, wake up. Oh, actually, speaking of the devil, that's the next topic. All right? Yes. Solving higher order homogeneous differential equations. Well, of course, guys, the 3 cases we just outlined in the previous few pages and we derived can be extended to differential equations of order 3, 4, 5, 17, 98, 20, 25th, whatever order you can create of an equation, you know. It doesn't have any limitations. All right? I mean, of course, I'm not going to give you a huge equation. Well, let's start with something kind of mild here, okay? So let's solve y triple prime plus 3y double prime minus 4y. Be careful here when reading these differential equations, guys, because we see a lot of y's, we see a lot of primes, and it's very easy to actually fall in some little traps right here. Something to notice, y double prime is missing. In quotation mark, not that it's missing, it's there in spirit, right? But it has a coefficient of 0, so it's there, yes. That's what I meant, but not what I wrote. Thank you, thank you. Yes. All right, well, let's write the characteristic equation, the auxiliary equation. So the third derivative becomes m cubed plus 3 times m squared plus 0m. Well, I'm not going to write that. And then minus 4 equals to 0. Okay, how do we solve this cubic equation? Well, whenever we have cubic equations, when we have the 4 terms, in some cases we can solve them by using factor by grouping. However, we only have 3 terms. So I don't think that's going to help here. Any ideas how to solve this polynomial equation?
Isn't there like a formula for exponent of 3?
There is a crazy formula involving crazy radicals. However, we're going to use another technique. Actually, a technique you know how to use. That's the rational root theorem. All right, how does that work? Well, so P, which is 1, and Q. Remember P over Q? Listing the potential zeros? Yes, these are coming back. Actually, P, this is P, and Q is the leading coefficient. Okay, so P over Q. This is plus minus 4 over 1, plus minus all the possible factors of 4, 1, 2, and 4, And all the possible factors of 1, well, that's just 1. Good. We don't have to test that many. All right? Okay, so this means the potential zeros are plus or minus 1, or plus or minus 2, or plus or minus 4. So actually there's 6 potential. That doesn't mean the equation has 6 zeros. I mean, it's a cubic and it has at most 3 zeros. Okay? So, well, let's test some of them. Typically, we start with the smallest of them, and I'm gonna start by testing m equals to 1. All right. Okay. Test. Well, test m equals to 1. All right. Well, what do? We're gonna use synthetic division to see the process. Yes.
I don't really get what happened after P over Q.
Oh, okay. So here, P, which is the independent term, the constant term, and Q, it's the leading coefficient. So what do we do here? We write all the possible factors of the number 4. 1 is a factor of 4, 2 is a factor of 4, and itself 4 it's a factor of 4. Okay. And then all the factors of 1, it's just 1, right? Okay. So let's write only a row of coefficients here. So that is the leading coefficient, which is 1, the quadratic coefficient, which is 3, the linear coefficient, it's missing, it's 0, and negative 4. All right? So let's write the number 1 outside. What do we do here? Drop the first coefficient, multiply these two, 1 times 1, drop, multiply, and add these two. 3 plus 1 equals to 4. 4 times 1, that equals to 4. Write it down below on the next column. 0 plus 4, 4. Now multiply 4 times 1 and put it below in the next column. What is 4 minus 4? Is that equal to 0? And that's what we wanted here. Because the fact that this is 0, this means this is what we're looking for. This means m equals to 1 is a 0, which also implies m minus 1 is a factor. Okay? M minus 1 is a factor. All right? So, now what does that mean? Okay, check this out. So, do you guys agree this is the coefficient of m cubed, the coefficient of m squared, the coefficient of m, and the constant term? The first 3 numbers are now the coefficients of the variable 1 degree less. All right? This is m squared, m, and the new constant term. All right? So every time we determine by synthetic division that whatever number we're testing is a 0, we degrade, or we annihilate annihilate the power of the polynomial. So this means, okay, let me actually write down the equation, the polynomial equation. M cubed plus 3m squared minus 4 equals to 0. This is the same as saying, well, because m equals 1 is a 0, that means m minus 1 is a factor, and then the other factor is whatever we got over here, m squared times 1, which is m squared, m times 4, which is plus 4m, and c times the constant, which is 4. And that is equal to 0. Okay? Now, forget about the cubic equation. Our focus now is going to be this quadratic. Okay, here is where, again, our factoring techniques are going to be useful. So hopefully this is factorable by the double bubble method, m minus 1. Hopefully, are there factors of 4 that add up to also 4? Plus 2, plus 2. Oh, repeat it. Okay? Repeat it. So this means, m equals to 1. Well, actually, I already had it, but I'm just restating it in the context of the solution to the equation to finally get to write our solution to the differential equation. And because these are repeated, this is m equals to negative 2 repeated. Okay? All right, we're ready to actually write the solution to, oh, this is equal to 0, to the solution to the differential equation. So y equals to c1 e to the 1x, which is just e to the x, plus c2 e to the negative 2x, however, plus c3, another e to the negative 2x, but what do? Multiply by a power of x. If we had, say, this m minus 2 repeated, say, 5 times, then we would need to go all the way to keep writing more powers of x all the way to the 4th power. We'll see an example like that later, right? Hopefully today. Oh yeah, we have plenty of time. All right. What's the next one? Yes.
Can you explain what the testing n equals 1 here?
Yes. Okay, so we write the coefficients of the polynomial equations 1, 3, 0, and 4. What do? Drop the first number, multiply with the number we're testing. Whatever you get, put it in the next column below, and then combine the numbers. That's going to give you 4. That number multiply with the number we're testing, 1. That's 4. Whatever you get, put it in the next column below the number. 0 plus 4 equals to 4. Again, keep multiplying by the test value, the test number. Whatever we get, put it below in the last column, in this case now, 4 minus 4 equals to 0. So because the last digit is a 0, that means this number that we're testing is a 0. If we have gotten maybe a 3 or something, this is not a 0, then it's not going to be a factor. We need to keep testing more of these potential zeros here. All right? So 0. Okay. All right, let's do another one. Let's see. So the fourth derivative of y with respect x plus 2 times the second derivative with respect x of y with respect x plus y equals to 0. So this is a fourth order differential equation. Okay, so let's write the characteristic equation. So this is m to the 4th power plus 2 times m squared plus 1. Okay, the coefficient of y without any primes or the like, that's going to be our constant term. Okay, and let that be equal to 0. Okay. Any ideas how to solve this polynomial equation? We can factor this one out, right? Actually, we can see this is a perfect square trinomial, right? We can see that actually m squared plus 1 and plus 1 actually, right? Okay. So what do we have? Okay, guys, check this out. So over here, because this is going to be repeated, okay? This is repeated. This will be m squared plus 1 equals to 0. And m squared equals to negative 1. That means m equals plus or minus the square root of negative 1. Which is m equals plus or minus I. And you know what? I think I'd rather write 0 plus or minus I, just so we can see the alpha plus minus beta I. All right? Okay. So this means, and well, this is actually repeated. Okay. So, okay, let me just state alpha equals to 0 and beta equals to, what is that? 1, right? That's the whatever I is multiplying, an invisible 1. Okay, guys, so because we have a repeated solution, if we had, okay, so that's going to be y equals to e to the 0x, okay, e to the 0x times c1 cosine x plus c2 sine x, okay. I'm going to need more space in here. And then, whoops, plus, if I write, okay, another e to the 0x, c1 cosine x plus c2 sine x, I would need to multiply by a power of x because they are repeated, aren't they? So this repetition not only holds for the real repeated, this also holds for the complex, or complex alpha plus beta ones, right? Well, e to the 0x, I mean, that's not much interesting about it. So this is just one. Maybe I shouldn't have even written it, but I just wanted to show you the whole picture. In the future, when you see when your solution is purely imaginary, you may skip the exponential. You don't need to write it because alpha equals to 0, e to the 0 is just 1, so it's kind of it's not necessary. It's unnecessary, especially when solving problems that similar problems to this are going to be longer. You may want to save some time. So this will be C1 cosine x plus C2 sine x plus x C1 cosine x plus C2 sine x. And you might want to distribute the x here. C1 cosine x plus C2 sine x plus C1 x cosine x plus C2 x sine x. All right? Solution. Now, if we had this repeated not just 2 times, 3 times, we would have needed to add one more. C1 x squared cosine, blah, 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 C2 x squared sine, blah, 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 and maybe repeat it 4 times. Okay, why not? Plus C1 x to the third cosine, blah, 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 C2 x cubed, sine, blah, blah, blah. Do you guys see the pattern? That's what I want to show you. What's the pattern? Well, in this case, this is just repeated once, repeated twice, repeated 3 times, etc. All right? And yes.
Why are the constants C1 and C2?
Yeah. About that. Okay. C3, C4.
They're not the same?
No, they're not the same. C3, thank you for pointing that out. C3 and C4. Thank you. Those are 4 totally different constants. And that's because we have a 4-order differential equation. So the order of the equation is the number of constants. Remember the linear combination, it has a constant for every function in the set of fundamental solutions. One more. Okay, let's keep going. Okay. Okay. Y triple prime minus 2y double prime plus 9y prime minus 18y. M cubed minus 2m squared plus 9m minus 18. Let that be equal to 0. Any ideas how to solve this cubic equation? Rational root theorem. I mean, do you want to do all the factors of 18? Okay, 1, 2, 3, 6, 9, 18. You don't want to test over 1, 2, 3, 4, 5, 6 times 2. You don't want to test 12. All right, but do you see anything else? I mean, you can do it. It's fine. Is there another way? What's that?
So 9's 2 and 18, so you probably factor out and then double bubble.
Factor out double and then double bubble. Factor by grouping, right? We can factor by grouping. M squared times m minus 2 plus m times m minus 2. Let that be equal to 0. And that's m minus 2 times m squared plus 9 equal to 0. Okay. Let's see. Okay. So from here, m equals to 2, and from here, m squared plus 9 equals to 0, m squared equals to negative 9, m equals plus minus root of negative 9, which is plus or minus 3i. Do you guys see how, again, we have the alpha equals to 0? So don't even bother writing that exponential factor here. All right. Well, let me actually give you the... Okay, no, never mind. So, the solution will be y equals c1 e to the first solution 2x plus, here we're going to form a combination of two terms containing a c2 and a c3 to combine with the imaginaries here. Well, actually, let me do the e to the alpha with e to the 0 x times c2 cosine 3x plus c3 sine 3x. All right. E to the 0x is just 1, an invisible 1. So that's c1 e to the 2x plus c2 cosine 3x plus c3 sine 3x. Final answer. Okay. And I believe I had another example. Okay, let me do two more examples. So actually, this is really the end of the notes, right? However, when I was preparing a class today, I came up with a couple of exercises. So you guys just use the back side of the page. Well, actually, you have plenty of space for one more here. So let's see. So let's do D. Okay. So that is y triple prime minus y double prime minus 14y prime plus 24y equals to 0. Okay, so we're going to do a few where we're going to practice our rational root theorem. All right. So, okay. So let's write the equation, the algebraic equation, that it's the auxiliary or characteristic equation, m cubed minus m squared minus 14m plus 24 equal to 0. Well, guys, unlike the previous example, we can't use the factor by grouping method to solve that cubic equation. So, well, I already spoiled it before, right? Rational root theorem. So let's list all the potential factors of 24. So PQ right here. Oh wait, no, that's fine. So P over Q. This is plus or minus 24 over 1 plus or minus all the factors of 24. That's 1, 2, 3, 4, 6 is 8 another factor, and then 12, and then 24 finally, right? Of course, I don't want to test that many factors, and in fact, I'm going to, you know what, I'm going to test one that is not going to work, and then, so you can see the difference. It's going to work as a review of the rational root theorem, because I feel like it's been a while since you did the rational root theorem, right? So let's get a refresher with an example when the zero works, when the potential zero works and doesn't work. Okay, so again, I'm going to test m equals to 1. Okay, I'm going to write the coefficient. So that is 1, negative 1, 1, negative 1, negative 14, 24, and 1. Okay, so drop, multiply, and add. 1 minus 1, that equals 0. 0 times 1, that equals to 0. Write it down below the negative 14. So that's negative 14. Negative 14 plus 1, that's negative 14. However, in the last column, negative 14 plus 24, that equals to 10. All right? Which is not equal to 0. So this means m equals to 1, not a 0. So we need to test another value. How about oh, okay. How about 2. Test m equals to 2. All right, so testing m equals to 2. Okay, let's write the coefficients. 1, negative 1, negative 14, 24. Okay, so 2, drop the 1. 1 times 2, that equals to 2. 2 minus 1, that equals to 1. 1 times 2, that equals to 2. Negative 14 plus 2, is that negative 12? And negative 12 times 2, is that negative 24? 0, okay? So 2 is going to be our 0. This means m equals to 2 is a 0. No. M equals to 2 is a 0. Let me leave some space for the degrading of the polynomial. And m minus 2 is a factor. Okay? So again, this is m cubed, m squared, m, and a constant. Now this is m squared, m, and this is the new constant. All right, what are we going to do? So let's go back to our polynomial equation. That is this one right here, and write it in factored form. That is m minus 2, that's the first factor we got out of the 0, and then m squared times 1, which is m squared, m times 1, which is m, c times the negative 12, but that's just the constant negative 12, equals to 0. All right? And what does that mean? Okay, so, so we already, can we factor this quadratic polynomial here? Hopefully not using the rational root theorem again, not without the need of setting up another synthetic division. Hopefully by the double bubble method here, we can find factors of negative 12 that add up to positive 1. What are those? Plus 4 and negative 3. Great. M negative 2. That equals to 0. Okay? So this means m equals to 2, m equals to negative 4, and m equals to 3. Actually, the 3 solutions are real and distinct. All right? So no multiplications by x. We're going to have an exponential for each, so no problem. Okay, let me add one more page here. And you guys might want to write all this, the next part of the problem, on the back side of the page. Okay, so our general solution will be y equals to c1 e to the 2x, okay, plus c2 e to the negative 4x plus c3 e to the 3x. And guys, does it matter if I'm writing the solutions not in increasing or decreasing, or no? It doesn't matter. It's because, this is addition of terms. Doesn't matter. Okay, guys. I mentioned before. I wanted to turn this into an initial value problem with conditions. Let me change the color for the conditions. Y of 0 equals to 2. Y prime of 0 equals to 1. Y double prime of 0 equals to 3. Okay? So, I'm going to use the first condition. Y of 0 equals to 2. Okay, so this will be y of 0, substitute 0 for the function, for the solution, c1 e to the 2 times 0 plus c2 e to the negative 4 times 0 plus c3 e to the 3 times 0. Okay, do you guys agree these exponentials raised to the 0 power are going to be all ones? Okay, so this is c1 plus c2 plus c3, but what's y of 0 equal to 2? Call this equation 1. All right. Guess what? Let's find the derivative y prime of the solution. Well, luckily for this one, we won't need to do any product rules. All right? So, yes. 2 e to the 2x minus 4 c2 e to the negative 4x plus 3 times c3 e to the 3x. Okay? There's nothing to simplify here, so we may use the condition for the first derivative at once. That is, with y prime of 0 equals to, what is that, 1? Okay. That should be, okay, y prime of 0 equals to, what is this? 2e to the 2 times 0 minus 4. Wait. I forgot the C1 here, right? 2C1. 2C1 minus 4C2 e to the negative 4 times 0 plus 3C3 e to the 3 times 0. Again, all these exponentials to the 0 power are going to cancel to simply 1 or reduce to simply 1. So this will be 2C1 minus 4C2 plus 3C3 equal to y prime of 0, which is 1. This is our second equation. Label the equation as equation 2. Okay? Second derivative, because we have a condition for the second derivative, okay? That is y double prime of 0, okay, equals to 3. So find the second derivative, okay? From here, this is the first derivative, find the second. Y double prime equals, okay, 2 times 2 is that 4 C1 e to the 2x minus equals to plus. Negative 4 times negative 4 is plus 16 C2 e to the negative 4x plus 3 times 3, which is 9 C3 e to the 3x, okay? And there's nothing to reduce. Let's just use the condition, the initial condition for y double prime of 0 equals to 3. And let's do the same. Y double prime of 0 equals to 3. Okay, so y double prime of 0, that means substitute 0 for the second derivative of the solution for C1 e to the 2 times 0 plus 16 C2 e to the negative 4 times 0 plus 9 C3 e to the 3 times 0. And again, all these exponentials raised to the 0 power are going to reduce to simply 1. And y double prime of 0 equals to 3. That is 4 C1 plus 16 C2 plus 9 C3, and call this your equation 3. Okay? So we have a system of equations with 3 equations and 3 unknowns. All right? How are we going to go about this problem? Okay, so let's write the system of equations first. Okay, so C1 plus C2 plus C3 equals to 2. 2C1 minus 4C2 plus 3C3 equals to 1. And finally, 4C1 plus 16 C2 plus 9 C3 equals to 3. And guys, you know a few methods to solve a system of equations with 3 equations and 3 unknowns. Elimination, substitution, Cramer's rule, Gauss-Jordan elimination. You learned that in pre-calculus, or those of you who are in linear algebra. All right. Also, finding the inverse of a matrix, which takes forever. However, for a problem like this, guys, I will let you use the graphing calculator. So what we're going to do here, we're going to encode this system of equations into a matrix, an augmented matrix. All right, 1, 1, 1, bar 2. All right. Or do you want to do Gauss-Jordan elimination? You want to do that one? Gotcha. 4, 16. Hey, that's fun. Yeah. And simply, okay. But I mean, if you guys are going to use the graphing calculator, at least show the system encoding into an augmented matrix, and show that you're doing RREF. Okay, let me go to the graphing calculator to show you the process in case you're a bit rusty on how to solve these systems. Okay, well, again, it's recorded, so you can watch it again. So, second quit. You need to access the matrix menu here. So, second matrix, and I'm going to edit. I'm going to edit 3 by 4 a 3 by 4 matrix. Oh, what am I doing? Okay, there we go. And I'm going to click enter. So I chose the second matrix, which is a 3 by 4. All right, so I'm going to input the entries that we had on the matrix. So, well, actually I already have something. Okay, the ones are already there for whatever reason. Okay, I'm going to change this to a 2. Okay, click enter, and then 2, enter, -4, enter, 3, and what was that equal to? 1, another 1. Okay, so that's 1. And then the last row, which is 4, 16, 9, and 3. Okay, so we're done entering all the values in the matrix, getting the entries. Okay, I'm going to get out of we need to get out of this menu. Go second, quit. All right, and then we're going to enter the matrix menu again. So second matrix, but now we're going to choose the operation we're going to do to that matrix. So I'm going to do math, the second column, which is the math operations. I'm going to go up a couple times until we reach the RREF. All right. Now I'm going to choose the matrix. I'm going to do the RREF. What does RREF stand for? Means reduced row echelon form. That's what it means. I'm going to get back to the menu, second matrix, and I'm going to choose the matrix I want to reduce, which is the 3 by 4 that already has the data store. Click enter, close parentheses, and you guys don't want to submit this as your final answer. Make sure to frac. Go to math, and the first option, which is frac, click enter again, and voila. All right. Okay, let's go back to the notes. Okay, so we need to write our reduce row echelon form matrix. And the solution here is, what was that? 10/3, right? 5 over 21 and -11/7. What does that mean? This means this is C1, C2, C3. Just like if we were solving for X, Y, and Z, except that we have C1, C2, and C3. We're not done yet. This is Y equals to 10/3 e to the 2x plus 5 over 21 e to the -4x minus 11/7 e to the 3x. Final answer. All right, final answer. Okay, guys.